All right, in this video, we're going to introduce another kind of paradigm for plotting curves. And in this one, we're going to completely change our coordinate system. So previously, we were looking at parametric curves, this idea of adding some sort of a third parameter that helps us describe the movement of the variables x and y as we move through our curve. And here we're just going to completely switch from the Cartesian or rectangular coordinates to polar or circular coordinates. So we'll talk about how to convert these coordinate systems back and forth. We'll talk about some of the features of polar coordinates, and then we'll just do a little bit of basic kind of polar functions, getting a feel for what those graphs look like, that kind of thing. All right, so let's get this started. Here's our basic idea for Cartesian coordinates. We know that we have this kind of rectangular grid. When we have our axes in our Cartesian coordinates, we've got like an x-axis and a y-axis, right? X is our horizontal axis, y is our vertical axis, and any point here, A and B, we just list it this way, where the first piece of our coordinates, the first component is the horizontal component, the second piece or the second component is the vertical component. And so we have all these points sitting on this kind of rectangular grid system that we have as we investigate x and y values of these points. We've got this special point here at 0, 0 that we call the origin, and then each point can only be expressed in one way. If you put a pair of numbers together, where one of them is the x value and one of them is the y value, you're going to get a completely unique point. And once you change those things, you're guaranteed to get a completely different second point. Now, with polar coordinates, things act a little bit differently. Instead of being plotted on a rectangular grid, we're plotted on a circular grid, where we have two components, r and theta. R is a signed distance, so here's our circular grid coming around this way. R is the distance that our point is from the origin, right? And theta is the angle from standard position. Now, when we say that r is a signed distance, that means that we could have a negative value of r here. That would give us the same angle where we shoot backwards through the origin. So that means things can get a little bit tricky. So again, we have some sort of a signed distance from the origin and an angular component. What we'll also notice is that inputs and outputs are kind of switched. Over here, x is the input and y is the output. And with our polar coordinates, theta is the input and r is the output. So we list it in opposite order, output, comma, input, for whatever reason. This point here in the middle, 0, 0, we call the pole, and then we can call the positive horizontal axis the polar axis. There's a whole bunch of terminology that we can get out of this. But one of the key things to notice is that there's actually infinitely many ways of expressing any given point. We can use coterminal angles. This value of theta we can increase by a multiple of 2 pi and end up at the same spot. Or we could go ahead and do an angle to here and a negative radius to shoot backwards through and end up at this same point. So there's lots of different things that we can do here to represent a single point. There's going to be infinitely many representations of each point. And that's a really big feature that's different than Cartesian coordinates. Let's just get some practice plotting some polar coordinates. We can take a look at a couple of different points. For instance, we could look at the point 3, pi over 4, and this point has a distance of 3 and our angle is pi over 4. Right now our tick marks here, or our grid lines for the angles, are in multiples of pi over 6, so pi over 4 is right in between. So we're looking at this point right here, because again, when we look at this angle, that's an angle of pi over 4, and then we've got this nice radius of 3. So there's 3 pi over 4. What we could also do, though, is represent this with an angle of, let's say, 5 pi over 4. Now, 5 pi over 4 puts us all the way past pi right to here, and we could use a negative 3 radius that would shoot us backwards this way. And this point is also negative 3, 5 pi over 4. We could go ahead and list a whole bunch of different points, right? We could look at something like, 1, 5 pi over 6. And that has a radius of 1, so it's going to be on this circle here. 5 pi over 6 is right here. because this angle is 5 pi over 6. So that's our 1 comma 5 pi over 6. We could look at negative 1, 5 pi over 6. And we're at this same angle, but now we have a negative radius, and so we go backwards over here. So things can get really crazy when we plot all these points. But hopefully that gives us a good feel for how this coordinate system works. We do want to know how to convert our coordinates back and forth from our regular Cartesian and XY rectangular coordinates over to our polar r theta circular coordinates. So let's just say, for instance, we have a point, I don't know, I'll just put it right here. We have a radius of 3. We have an angle of pi over 3. Let's say we want to convert this to x and y coordinates. What we need to do is to come up with this vertical component and this horizontal component. And you can see that that's not going to be super easy, right? It's going to be some number in between 2 and 3 for the y value and something in between 1 and 2 for the x value. It seems like this could be really tricky to do until we just notice that if we drop a line down and over, suddenly we have a right triangle. And if this is the x value and this is the y value, and we know that this radius or hypotenuse is 3, and we also know what this angle is, pi over 3, then we can just use some basic trig functionality here, right? We can pretty clearly show that x, well, maybe I'll say cosine of pi over 3 is going to be x over 3. And so we have that x is equal to 3 cosine pi over 3. And we can also pretty clearly see that sine of pi over 3 is equal to y over 3. So y equals 3 sine pi over 3. So we can get these x and y values without too much trouble here. We hopefully know that cosine of pi over 3, this here is really just a half. And so our x value is 3 halves. And hopefully we know that sine of pi over 3, that's really going to be root 3 over 2. So our y value is 3 root 3 over 2. So we can convert this way pretty easily. In general, what we have is that x is always equal to r cosine theta, and y is always equal to r sine theta. Similarly, if we have the x and the y values and we want to figure out what the polar coordinates are, what r is, we could go ahead and draw that situation as well. We could say, let's pretend we have some point at, like here, -2, -1, we'll say. So maybe right around there. It's a little hard to draw. And that's in our Cartesian setup, right? Maybe I'll do this in blue because it looks like I'm doing blue for my x and y values. So this is -2, -1. And let's say we want to find the polar coordinates. We can do the same thing, right? We can draw our triangle here. And we can say, all right, we've got a right-angled triangle. But now we have side lengths of our triangle. That's -2, -1. And we want to find the radius. Well, that's pretty clearly going to be just the Pythagorean theorem on this thing, right? So it's one side length squared plus another side length squared is going to give us the square of the radius. So we can see pretty clearly in this case that r squared is going to be 4 plus 1. So r has to be the square root of 5. Now, technically, it could be positive or negative, right? So that's going to depend on what we choose for our angle. And then for the angle, what we can do is just figure out what this reference angle is, right? Maybe we'll call this alpha. And that shouldn't be too bad because we know two of the side lengths, x and y. So we can notice that, well, wait a second, tangent of alpha equals half. So that means alpha is tan inverse of half. And then you could go ahead and say, like, well, since we're over here in this quadrant, we could add pi to it. So theta in this case is, pi plus all that. What you'll notice is that things work out really, really nicely with the tan inverse function. It's only going to give us some specific values, and so we can go ahead and just make sure that our radius is going to match for that specific output of the tan inverse function. Our tan inverse function only gives us values between negative pi over 2 and positive pi over 2. It's only going to give us angles over here. So again, we could either go ahead and just add 2 pi to this, or we could use the negative radius for this, right? So we could say, well, this point is really, our r value is negative square root 5, and the angle is tan inverse half, whatever that is. I could evaluate it and round it off to some decimals or something like that. It's not a nice one that I really know off the top of my head, so I'll just leave it like that. Or you could say it's square root 5 pi plus tan inverse half, right? To make sure that you do get all the way around to this thing. So in general, what we can do is we can say r squared is x squared plus y squared, and tan inverse of theta is going to be our y value over our x value. And this is, again, just by drawing these little triangles on here. So I can't state this strongly enough. Anytime you want to do some conversion with coordinates, just grab your point, grab the origin, and draw this little triangle, plug in whatever information that you know, and suddenly you can do whatever trig stuff you want to do to figure out what's happening here. So this little triangle picture where this is y, this is x, this is r, and this is theta is really, really helpful for us. Now you might have to fudge things a little bit if you're in a different quadrant like this, but no big deal. All right, let's take a look at some graphs, right? We mentioned earlier that we're going to be thinking of theta as the input variable and r as the output variable, meaning these functions are going to look like, instead of y equals f of x, it's going to be r equals f of theta. So let's take a look at some of these types of functions and just investigate and think about what their curves are going to look like in polar coordinates. So here's a couple of easy ones. Let's just take a look at the two constant functions, r being some fixed value like r equals 4. Well, what this means is that we have a radius that's 4 no matter what the angle is, right? So it makes sense that this is a radius, or a circle, sorry, with a radius of whatever the absolute value of a is, right? If r is negative 4, then that means that we're just backwards through the origin, right? But that's fine. We're centered at the origin with this radius of absolute value of a. And similarly, if we have theta being constant, like theta equals pi over 3, then that means that no matter what the radius, that signed distance from the pole is, we have the same angle. And so it's just a straight line crossing through the origin at whatever that angle is, or maybe we could call it the pole instead of the origin. Linear functions get a little bit trickier. What happens when we have some constant radius plus some coefficient on theta here? What this means is that we start at whatever this constant value is when theta is equal to 0, but every time we move this way, we're adding or maybe subtracting, depending on what a is, some sort of a distance. So we're going to end up with some sort of a spiral thing. It might look like this, where as we move around, we get further and further away, or maybe it looks like this, where as we come around, we get closer and closer and closer. So we have this offset b from the pole. That's always just going to be like a starting point. You can think of it as an intercept, but now it's not a y-intercept. It's whatever we are on the polar axis, this positive horizontal axis, when theta is 0. And a is just some sort of a scaling or rate factor for the spiral that also impacts the direction, like does it spiral towards the pole or not, things like that. So hopefully that's helpful to see a little bit about what's going on with that. We also can look at general circles here. R equals 2a cos theta plus 2b sine theta is the general form of a circle centered at that point AB with the radius of the square root of a squared plus b squared. Ugh, that's kind of awful. What you can notice is that if a is equal to 0, right, then what we end up with is r equals 2b sine theta, and our radius is just the square root of b squared. And so it's a circle centered at 0, comma b with radius equal to b. And similarly, if b is equal to 0, then we get that r is 2a cos theta centered at a, comma 0, where the radius is a. So these are very two specific cases, but let's take a look at the general form of this, and let's just kind of build this thing. So we want to justify this general circle formula to see how we can derive this and make it look like something that we recognize. Normally, when we think of our circle formula, this is what we think of. X squared plus y squared equals r squared. We could add all the shifts in, and then we end up looking like this. X minus a squared plus y minus b squared equals, we're looking for a radius of the square root of a squared plus b squared, so I'll just say a squared plus b squared. That's what we have that we're looking for in this case. So what we want to do is see if we can connect these things. So the way that we'll do it is we'll multiply r on both sides of this. So we end up with r squared equals 2ar cos theta plus 2br sine theta. And then you might remember that we said r cos theta and r sine theta, weren't those our values for x and y, right? If we go back up here, that's what we're looking at right here. So we can just do a little bit of substitution here, and we can say this is really r squared equals 2ax plus 2ay. We can think, wait a second, we know what r squared is. This is x squared plus y squared. That was our other part in our formula. So what we have is x squared plus y squared equals 2ax plus 2ay. Now, if we move everything over to one side, we end up with x squared plus 2ax plus, I'm going to leave some space, you'll see why in a second, y squared plus 2ay equals 0 right now. But what I'm going to do is complete the square on these. So I'm going to complete the square on this, and I'm going to complete the square on this. If we complete the square here, we need to add in some other term that's going to make this a perfect square. Let's add in a squared here. That's going to make this x plus a squared, right? Oops, my signs are off. These are supposed to be minuses because we moved them over. There we go. That's better. And then we're going to add an a squared over here as well. Similarly, we're going to add a, oops, and this is supposed to be a b. There we go. Similarly, we're going to add a b squared. And now suddenly, this is x minus a squared plus y minus b squared equals a squared plus b squared. So we can see horizontal shift, vertical shift. So this thing is centered at a, b, and we can pretty clearly see that r squared is equal to a squared plus b squared. So that means r is the square root of this thing. So if you want to draw a circle in polar coordinates, this is what the function looks like there. So those are just a couple little things just to start getting used to working with these, the conversions between them, all that kind of stuff. You can take a look at the curves of these by just plotting these functions, and like normal, you might have to change a setting on whatever graphing calculator you're looking at, or if you're on like Desmos or something like that, I think it'll automatically understand what you mean if you type in r equals, 2 cosine theta plus 2 sine theta. It'll know, oh, okay, this is in polar coordinates, and graph that. Or you might just need to change a setting somewhere. But you can graph these just like you would normally, and things go pretty well from there. Instead of spending a ton of time on graphing these polar coordinates, which there's lots of resources, other places to do that, what I want to do is just jump right into talking about calculus on polar coordinates. So we'll do that in our next video. We're going to talk about rates of change. We're going to talk about slopes of tangent lines. And we're going to talk about areas under curves and definite integrals, just like we did with the parametric functions. So let's go ahead and do that.